Welcome back. We're in Projectiles Unit Worksheet 3, problem number 4 here. Let's get into it. A bullet is fired with an initial velocity of 390 meters per second at an upward angle of 30 degrees from the top of a tower, 500 meters above the ground. Here's a whole bunch of, we kind of want to know everything. How long will it rise? So time, I'll put notes off to myself here. Time is question mark. How far up will it go from the top of the tower? So like y max, you might say. What's the total time in the air or hang time, the flight time? You know, in the air is a little bit ambiguous because then you're thinking, hey, is there air resistance? And the answer is no, we're not doing air resistance here. So careful with that. What's the range? That's my delta x there is a big question mark. So, and how long will it rise? It's like t to the peak there, TP, sometimes people do it. So yeah, let's draw it out. As we know, drawing this can be very, very helpful. So, and this is a cannon. No, it's a bullet. Yeah, it's a bullet. So somebody's defending some sort of tower here. So we make like a tower. I'll make it like slightly three-dimensional here. Here's the ground. I'm signifying it's the ground, and movable object with these little slash marks there. There's like, this is a tower, so it looks like a turret. And old medieval turrets had like little, I don't know what you call those, little teeth that came up. I'm sure there's a name for them. So people can like hide behind them and not get shot by everybody else. Anyway, somebody's up there and they are firing upwards. I guess they're way bigger than these little teeth there. I should have made those teeth bigger. Whatever, it doesn't matter. They're firing upwards, and I'm not going to try and draw such a small gun there. I probably should have made my diagram a little bit bigger. Yeah, here's a note. Make your diagrams bigger, otherwise this happens. So then it's fired 30 degrees upwards. 30 degrees is, I don't know, something like that. And so V naught is 390 meters per second. And I'll put in the component vectors here. And the angle there, angle is 30 degrees. Back to green, and this is going to be 390 cosine of 30 degrees. 390 sine of 30 degrees. I make sure that it is an angle upwards. Yes, it is. 500 meters above the ground there. Let's go, that's an important bit there. So this distance right there, that height there is 500 meters above the ground. I'll go draw in the path that this thing is going to take. It's going to be some sort of parabola, looking something like that. I got to extend my ground here. And I'll even label the things that I don't know on here because that's going to be important. Bullet looks like it fires right about there and ends over there. Delta X was one of them. That was the last one. Why am I doing that first? I don't know, because we usually are trying to figure out the horizontal range. How far up will it go? So that's like right here-ish. And so we're looking for like Y max is a big question mark. How long will it rise? So that's like the time to the peak there, so I still don't know that. How long will it go for? That's the time over there, the total hang time, and that's it. I'm looking for those four things there. Okay, great. So now, as you can see, more complicated things makes it a lot nicer to draw a picture. We'll make an x dimension and a y dimension as these motions are independent of one another. Make my y dimension a little bit more room because I usually do more work over there for that. My delta x, I can start on either of these dimensions. I almost always start on the x dimension. Why? I don't know. Usually we're looking for some horizontal range, or maybe a lot of times it's just easy. I guess maybe because it's easy, and it's good to get some confidence booster right there. We know the acceleration of the horizontal dimension is 0 because nothing's pushing or pulling it. We don't know the delta x. And we know the initial velocity, again, that's in the x dimension there, so I'm explicit about that here, just for you, multiplied by the time. Now, I don't know the time that it takes, nor do I know my v naught x, nor do I know how far that thing goes. Man, I don't know a whole lot of things. So, it looks like I'm stumped there. So, that's okay. I'll just go over to the y dimension and see if I can figure out anything over there. Delta y is 1/2 at squared plus v naught t. Now I look at that and go, do I know any delta y's? Well, I know something about the y's. I know the original y was, oops, sorry, not 0. It was 500 meters. Okay, so I know the original position, but I don't know the ending position. Nor do I know even the y max. Actually, I'm looking for the y max. Maybe I can go find the y max in this one. What else do we know here? Let me change out of black. We know the acceleration is negative 9.8. I don't know the time. I don't know the time to any of these things. And I do know the velocity. The velocity is just going to be that 390. Oh, I do know the original velocity in the x dimension there. Why did I say I didn't know that? I don't know. 390 cosine of 30 degrees. And this one over here in the y dimension is 390 cosine of 30 degrees. Okay, so, well, you know, here again in this vertical, or I have two unknowns here in the vertical dimension here. I don't know time, whether that's to the peak or the whole time there. Peak is probably going to be easier to find because I know some other info about that. And I don't know the delta x. I don't know the delta x to the peak, nor do I know the delta x to the end there as well. So otherwise I could like combine those and find that. But I can't combine these equations because I have different variables. I have the same time, which is nice, but I have like different y's and different x's. So those are two different variables. So now I have three variables and two equations. I can't do anything with that. However, maybe there's something else I can look at here. So I keep thinking and go, hey, in the vertical dimension, I do know that the velocity is equal to at plus v naught. And let's see if we know any of this stuff. Well, one of the things we're trying to figure out is at the peak there. And at the peak there, I do know some things. Remember that it's not rising or nor falling right at the peak there. So my velocity in the y dimension is momentarily 0 there. Okay. So if I was trying to find the peak, this would be like TP for the peak. Then this velocity, I should do that in a different color. That velocity right there, this one right here would be 0. We know that acceleration is negative 9.8. I don't know that time. That's okay. I'm trying to figure that out. And I do know this original velocity, which is 390 sine of 30 degrees. So cool. I can solve for the time it takes to the peak there. So I'm going to go and algebraically rearrange this so I get v minus v naught over my acceleration is equal to the time to the peak there. So I'm just subtracting and dividing there. And then I put in all my values, 0 minus the 390 sine of 30 degrees, and then divided by my negative 9.8. I look at that and go, that works out because I have negative and negative in the numerator and denominator. So that works out to be a positive time, which I expect I'm going to get a positive time. I pick up my calculator and go do 390 sine of 30 degrees and divide it by 9.8, and I get 19.8. Did I do that right? Am I in degrees? Yes, I am. It's just a really fast bullet there. 390 is really fast. And so I'm in the air. The time to the peak is 19.90. 19.90. It's going to round there. And I go and store that into my calculator because I'm probably going to use that time later on. And that's the time to the peak, so I label it as TP there. And then I go, what else do I want to know? Well, at the peak there, I also want to know how high it goes. Well, go back to my delta y equation right there. If I take this TP and I plug it in there for the time, and I plug in, and let me do that in the other color, I also know some of this delta y. I don't know the ending position, it's like y max, but I do know the beginning one, which was 500 meters. Okay. So now I'm just going to put in and solve for time there. So I'm going to put all that stuff in. That's a quadratic equation. So I'm going to put all the stuff in and then rearrange a little bit there. So I'll do that in black. So I got y max minus 500 meters equals my half, negative 9.8. I'm going to drop the units actually. Let me get rid of those meters there. My time was 19.9. Square, again, I'm using the whole string of numbers there. I am not using that rounded value, sine of 30 degrees, and then that whole thing times my 19.9. Man, I'm running out of room there. All right, so then I just add my 500 over to the other side, so y max is going to be, take that 500 and add that over to the other side there. Cool. So now I just put that in my calculator. Luckily, I already stored that time value, so that makes it much easier. Careful that that acceleration is negative there. That's easy to miss. So t, I square it, plus my 390 sine of 30 degrees, multiplied by the time, and then don't forget to add my 500. And so I get 2440.05 meters. And I think to myself, that's really big. So I go back and I look at my my stuff that I just put into the calculator, put it all in as one line there so I can diagnose things. I can see if I did everything right. Make sure that the acceleration is negative there because that's going to decrease the overall value. And I recognize, yeah, it's going to be a whole lot because this time is really big. So looks like I didn't make a mistake. I think that's actually the Y max there. So that was one of my answers there. Oh, and so was this time there as well. So I'll go ahead and box those two. So that's the time to the Y max and the time to the peak, or time to the Y max. That's true as well as how high it goes, the Y max. Now we need to figure out when it gets down to the ground there, though, as well, the time and the horizontal range, the distance that it goes to get down to the ground there. So I'm going to go ahead and divide this. We're still working in the Y dimension here, but I'm going to separate those calculations because now we're going to go to the end. So back down to the ground. So maybe I'll make a note to myself, to the ground. That's what we're doing these calculations for. Now, when it gets down to the ground, do I know anything about it? I don't know. Let's delta y is 1/2 at squared plus v naught t. Let's go through this one more time. Do I know anything about this? Well, down to the ground, I look back at my picture. Do I know anything about delta y when it gets down to the ground? Well, I know that the beginning position was 500 meters. And I also know that my ending position, if I label the ground here as 0 meters, which most people would in this problem, if I label that, then the ending position is 0 meters, because we're talking in the vertical dimension there. So here, I do know this. That is ending 0 minus the 500. So we get negative 500 for that. Cool. The acceleration is negative 9.8. We don't know the time. We do know this guy. That was the 390 sine of 30 degrees. And so now I can actually go and I just solve for the time. So I go and do that. I'm going to add my 500 over to the other side. And I'm going to rewrite, I don't know, why am I rewriting this? That's okay, I don't know. So we can set up the quadratic equation here, and you can see to make sure that you are setting it up correctly. Maybe that's why I'm doing it. Yeah, that's why I'm doing it. Yeah, good on me, smart man. Okay, so I add the 500 over to the other side. I do that because now, when I go to solve quadratic, it's way easier to do that when it's set equal to 0. Remember that you can go back and you can use the equation solver in your calculator to go do that. So I'm going to go ahead and I'm going to do that. Oh, I'm going to go back to the home screen here and grab my emulator here. Now I know that this is going to be rotated when you're looking at it. Sorry, I don't have any way to solve that. Oh, the solver. Will the solver solve it? No, it won't. Anyways, half times negative 9.8 is negative 4.9, so I'm just going to do that straight away. Multiplied by the variable squared. I'm just going to use x because I can just press the button that's right next to alpha as x, so it saves me a button stroke there. Add that to, if I recall correctly, is 390 sine of 30 degrees. And then I got to multiply that by the variables there as well. I'm going to choose x, and then I had to add the 500 over to the other side. And I'm pretty sure that I did that correctly. I double checked to make sure that my calculator is in degree mode. Yes, it is. I press second mode for quit there, get back into this, the solver there. Again, if you'd not followed along from before, if I hit the math button right underneath the alpha button there, and then scroll down to the bottom, which is the same as just pushing one up to the top, and then I get down to the bottom, and then go to solver, then I get straight there. If you're on this screen right here, this is the maybe answer screen, and if I press up, it'll get to the equation that's right there, and to edit that. If I want to get back down, I can press down, and then it goes to the next screen there. Now remember that you are expecting 2 solutions to this second degree polynomial. Well, where are those solutions coming from? Well, they're coming from the guess here. well, or it's giving you only one of them at a time, and it's giving you the one that's closest to the guess. Whatever number you have in here is your guess. So, it's right now it's just whatever X was stored at in the calculator's memory. So I'm just going to put in something. I know I'm looking for the positive value because I'm not looking for negative time. That doesn't make sense here. And I put in 10, and it gives me a time of -2. Well, that's the answer that I don't care about. So I need to put in a guess that's bigger. So I just put in anything bigger, put in 99 because it's easier to type in than 100. And boom, I get the other answer that was closer to 99, which is 42.21 seconds. And so now I'll go back to my paper, 42.21, and I get this rotated properly so that you can see it properly. And I find some time value, t is equal to 42.21 seconds. Cool. And right now it's stored in my calculator as x, and so I can use that later. So that is the total time, and I'll even put total down there just to remind myself and the reader that this is the total time. And then we're also looking for delta x there. So let's go ahead and let's take this total time and plug it in there for t, and that'll give us our delta x there. So I find delta x is just that time value multiplied by 390 cosine of 30. Flip back to my calculator, and that becomes very easy since I have that stored. This is notice how the calculator says x is equal to 42.21. So that's what it's stored in the calculator as. So if I press second and then quit, I get back to the home screen there. And so we said we needed to do 390 cosine of 30 degrees and then multiply that by the time value. The time value is already stored in the calculator as x, so I can just put multiplied by x, press enter, and then boom, there I go, 14,257 and a half. 14,257 and a half. This is still thinking about it. 14,257.50 meters, if I recalled that correctly. Boom. And that's it. We reread the problem, and I'm pretty sure I got everything. We got how long will it rise up? Yep. We got the how high will it be, what's the total hang time, and its range. We got everything. That's it. Have a wonderful day. See ya. Bye.